Okay, so now that we've sort of can't say nailed it, but we've tried to figure out or try to understand, okay, 3D flow past a coordinate and angle of attack, okay, and we saw that unlike the axisymmetric case, right, where we were basically dealing with just one independent variable, right, which was the theta. Then we came to the coordinate and angle of attack, and we saw that the flow was still conical, and meaning that the properties, we took a spherical coordinate system where the properties would still be constant along the radial direction, but would vary on the projection of that, okay, which is in theta and phi directions, right. And we tried to see if you understand what that means in a 3D space geometry wise, and so on and so forth. Okay. And I tried also to give you a brief overview of a numerical procedure in which the way which one could implement in order to study the properties across such a flow. Now, so essentially the first one where we had the axisymmetric case, we had just one independent variable, and this is also a 3D flow. The next one, the angle of the coordinate and angle of attack, is also a 3D flow. Here the number of independent variables is 2, theta and phi, right. Now, so when we say 3D, so when we say we are going to graduate from 2D to 3D, we are basically looking at 3 variables. Numerically, that is what we would say, right. So, let us look at something like that. We would have a real 3D flow with 3 independent variables, which we basically, if the body is a blunt nosed body, okay, at an angle of attack. Okay, and let us see how the governing equations would look like. Okay, we'll start with a small figure, and guess I am not going to the detailed geometry the way we try to understand it for the coordinate angle of attack, but hopefully you will be able to visualize that a little more now. And what we are going to use here is cylindrical coordinates. Okay, so let us see what I mean by that. So, okay. So, let us say I have something like this. Okay. Okay, there we go, and okay, somewhere over here. Yeah, that's more like it. Okay, so okay, and this would be more like the free stream, which makes an angle of attack alpha, right, like this, and this is again C. Okay. We will call that as C. Now, okay, I am basically looking at a plane like that. Okay, so I am looking at a plane like this. Okay, and I draw and I take basically a radial vector like this. Okay, I take a radial vector like that. This is R. Okay, so this is R. So clearly, now this angle is my phi. Okay, this angle is my phi. So hopefully this makes a little bit. This is also sort of you take this radial vector and rotate it. Okay, it's just that you can see that here the radius is going to sort of differ as we go along. Okay, so so this is the phi geometry wise, and let us draw some velocity vectors. Okay, let us draw some velocity vectors here. So if I were to look at, say, this point in space, okay, so this would be VR. Okay, this would be VR in this direction would be VC, and okay. So this is what we are looking at, a cylindrical system of coordinates. Okay, this is a okay, basically R, phi, and Z. So, we in this particular case, so R, the phi and the Z, right. So, this is so let us see, therefore, if I were to write out the governing equations in this system of coordinates, what that would look like. Okay. So, like we did in the previous case. Okay. So, let me write that down. Okay. So, again, so this will look like this, continuity okay. Let us call this as 1. Okay, that is what the continuity looks like. Then we will take momentum. Okay. So, momentum first off in R direction, momentum in the R direction, right. Now, that looks like okay. That is rho okay. 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 So, that is the momentum in the R direction. Then in the phi direction, okay, in the phi direction, okay. Yeah, that is the in the phi direction, and finally in the Z direction. Okay, that is Okay. So, these are the momentum in the r, phi and z direction, and the energy. Finally, the energy Okay. So, then we have the phi by r Okay. So, these are our basically governing equations, right, in the cylindrical coordinates. Okay. Now, numerically, how do we go about solving this? Now, first things to do is you have to transform these equations onto a rectangular coordinate system. Okay. What does that mean? Okay. So, what does that mean? In order to do that, we will have to use some kind of transformations. Okay, we've done a little bit of that when we did linearization, right, and we transformed into the zeta eta space. Okay, if you remember. So, we're going to do something like that to transform this space into more of a rectangular system of coordinates in order to be able to implement this numerically. And we will take, and the shape here, shape of the body doesn't have to be, in this case the way I have drawn it is like symmetric. It doesn't have to be, it can be any arbitrary shape. Okay. So, let us say that we will so hope you understand this here. So, we have a blunt nosed body over here, we have a blunt nosed body over here, and we will have a shock wave which will come somewhere, which will be generating from here. Okay. So, so therefore, here let us get a transformation for here, for this. So, in order to do that, let's say the shape. Okay, let me write this here. Let's say the shape of the body. Okay, the shape of the body we will define as, right. So, the shape of the body is z is equal to a function b, okay, and b basically for the body. Now, this in this particular case I have taken it axisymmetric, which is why I write it like this. It does not have to be, it can be anything. Okay. So, let us just say, so in here let me write the shape of the body, okay, as say some function, which I am calling it as b in this particular case, and then the shape of the shock wave, okay, shape of the shock wave okay. So, let us call that okay. So, here of course, the shock wave is a function of r phi, and it's time dependent. So, the in here clearly the shape of the body being axisymmetric is just a function of r, okay, z is equal to r. The shape of the body does not change with time. I hope that's clear, right. So, then the shock wave, however, now when I define the surface of the shock wave, so I call that as some function s for shock wave, right. So, this is arbitrary shape, we do not know what. So, it's function of r and phi, and also changes with time, right. So, this is if we define this, okay, if we define this, then we will, now let us go and calculate this. Okay. Now, we will just say, let us consider just this. Okay. Let us consider the s to some delta, okay, delta to be equal to this. Okay. So, this is essentially the space between the shock and the body, right. So, this is the or say if I were to write this a little more. So, say delta okay. So, if I were to write it like this, okay, if I were to define this as I am defining, you can see here just geometry. Okay. If I were to define this, then we will now set some independent variables. Okay. So, let us now define a new set of independent variables. Okay. How do we define that? Okay. Delta okay. So, essentially this is the spatial coordinates, okay. Time is time. So, now the independent variables, so we have a tau, I think, right. So, this tau is z minus b by this delta out here, y is equal to r, x is equal to phi. So, let me draw this. How would this look like? So, we basically going to draw say cylindrical coordinates, right. So, which means okay, this then let us call this as the origin, okay, and this is the tau direction, okay. This is the y direction, okay. I hope my artwork is more or less okay. All right. So, this is it, and this is my x. Okay. So, if you look at this, so this is basically the transformed coordinates. So, the way I transform this over here, so this is the tau. So, this is my tau over here. So, basically now the body and the shock, I'm observing that sort of I transform it to this three-dimensional coordinates, which is this tau x and y, and this tau out here is z minus b by delta, y is equal to r and x is equal to phi. Okay. So, if you were to essentially look at this, so what we are looking at is that this is the body surface, okay, on this face, and this is the shock surface on this face, right. This is the shock surface on this face. Okay. And so, so this is my geometry, okay. And some more transformations, the dependent variables, okay, we will transform the dependent variables as, let us call these, okay. 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 So, which essentially meaning that when we had pressure, density, etc., in this coordinate system, what will that be in this coordinate system? So, we transform the dependent variables in this fashion. Now, if we do that, then the governing equations, right, the governing equations which we wrote in terms of say density V r, V phi, V z, etcetera over here, right. So, we wrote all these terms V r, rho, V phi, V z, etcetera. See all these terms, what happens to these? Because these are no more there in this particular coordinate system. So, now with our transformations, the governing equations also change, right. Governing equations also change, and so let us just see how what they look like now, okay, how they look like now. So, let me write those down, okay, let me write those down, and okay. So, what I am going to do is write it right next to the equations in the cylindrical coordinate system. Okay. So, we will write it there, so that it kind of you can make a quick comparison. Okay. So, the continuity, okay, same the continuity you can write as, and I will write all the time dependent values, time dependent derivatives on the time derivatives on the left hand side. Okay. That is how I am writing the equations. Okay, and let us call this as say 6. So, this is our new continuity equation. Okay, this is our new continuity equation. Again, now momentum in r direction. Okay, momentum is, so this is the continuity actually. Okay, then momentum in r direction. Okay. So, if I write that, okay, okay. That is in the r direction, then in the phi direction. Okay, in the phi direction, okay, and in z direction. I think it's important now, so that for you to compare the two sets of equations and see that how the derivatives of all the velocity components Vr, Vp, Vc, etc., they look like in these set of equations in the cylindrical coordinate system, and what are we doing with those in the corresponding equations in the corresponding rectangular system of coordinates into which we have transformed our space. So, I think just sort of make a quick comparison between the two. Okay. So, finally, the z, okay, okay. So, these are essentially the equations, and we have got one more, the energy equation, right. So, let me write the energy equation. Again, so here okay. So, where you can see we have these constants A, B, C. Let me quickly write that down, what that means. Okay. 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 So, that is essentially our the governing equations in the transformed coordinate system. Okay. So, they look like this, and as you can see, I think this is a time where we tend to have a little more respect for our computers, right. To solve these equations, you need to solve these equations on this rectangular computational grid, okay, and solve for your properties, okay, for this blunt nose body in a supersonic flow. Okay. So, let us again go ahead and see how we will do that. We will illustrate the steps of doing that, which is pretty similar to what we did for the coordinate and angle of attack. So, let us sort of take a relook at that. Okay. So, essentially what we are saying now is that when we implement this, okay, when we implement this problem, okay, so that is we have a blunt nosed body, and we have a supersonic flow in here. Okay. So, then the equations, the governing equations look like this. It's as simple as that. The governing equations look like this. Okay. So numerically, what this means now to numerically solve this problem is that we have these set. This is my equations to solve. Okay. And physically, what this means is that now these equations result after transforming our governing equations from the cylindrical coordinates to a rectangular system of coordinates. Okay. Okay, so all right, so step 1. Okay, so how do we go about this? Now, if you look here, so essentially, so all these the time variants are all on the left hand side. Okay, time variants are all on the left hand side. Well, I think I can write the first one. Okay, I missed the equal to sign over here. This is equal to. Okay, all the time variants are on the left hand side. So, the first things we will do is assume the flow at time t. Okay, so we will start by so we assume the flow at time t. Okay. So, now if you look at each equation on the right hand side, we have the derivatives. Okay. We have the derivatives of the flow field with respect to x, y, tau, etc. Isn't it? That each and every equation here on the right hand side basically consists of the derivatives of the flow properties in x, y, and tau directions. So, we have the derivatives of the flow properties in space. Now, what we will do here in step 2 is having assumed the flow at once we assume the flow at time t, we will get the derivatives of the flow. Okay, we will get the derivatives of the flow, which are these del r, del t, del v r, del etc., etc. We will get the derivatives of this using finite differences in space on the right hand side. Let me clarify. So, let me first write this down. Okay, so at time t. Okay. So, spatial derivatives, okay, calculated using finite differences, right? Finite differences, okay, finite differences in zeta, x and y coordinates, isn't it? Let us just call this. Okay. This here. So, okay, so let us say I am calling this as say step 2. So, at this particular time, the moment you assume the flow field, you calculate the spatial derivatives, okay, spatial derivatives here, okay, in the in this coordinate system using finite differences. Okay. Once you do that, then calculate the time derivatives using the equation 6 to 10. Okay. So, then we calculate the time derivatives, okay, of basically say of r, okay, Vr, Vphi, Vz and psi. So, which is what is given by, okay, So, then we compute the time derivatives of this, which is what we get is del r del t, del v r del t, del v phi del t, etc., from 6 to 10. Okay, makes sense. And then the next step is, so therefore, now having done that, we will march the solution in time. We will march the solution in time, okay, using the predictor corrector approach, which I briefly talked about yesterday. Okay. So, the next thing is okay. So, what do you see over here? So, essentially by this time what I have done is calculated, I have just assumed the flow, okay, and I have calculated the derivatives of the flow at at time t. Okay. So, clearly that is not a that is not the correct values, or it is not the exact value that we are looking for, because we have just assumed it. Okay. So, what we will do is march the solution in time. Okay. Yeah. Okay. So, march the solution in time, which means that now we will find out the flow properties at time t plus delta t, right. So, using the predictor corrector approach. So, let us just go and talk about that a little bit. Okay. So, let me erase just this, because I am going to use these equations, so it is important for you to see. Okay. So, these are the equations that we are using. So, we are using 6 to 10, we are using these equations out here. Okay. So, how do we do this? Okay. So, now this okay. So, let me call any of these parameters here, or properties R, VR, Vp, Vc and psi. Let me call that as, say, let me just give that a name as G. I am going to just call that is G. Okay. So, G could be anything, it could be R, VR, anything. Okay. I am just giving it a random name. Okay. So, in here, so what we will calculate is, okay, here what I will calculate using 6 to 10, right, 6 to 10, we will calculate this del G del T, okay, using the using forward differences in space on the right hand side. Okay, right hand side. So, okay, so how do I, okay, let me write that down. So, calculate, okay, what this means is that we calculate, okay, del G del T from, right, 6 to 10. Okay. Using forward differences, okay, in space, actually in space, okay, on right hand side, okay, from known flow field. Okay. At time t. Okay. This is what we have done actually. So, we calculate the the derivatives, the time derivatives of the flow properties, okay, using finite differences in space on the right hand side for the known flow field at time t. Then we calculate the predicted value. Okay. Then we predict the value at t plus delta t as follows. Okay. So, predicted value Okay. So, predicted value, and we are going to call that as say g bar, I am going to just call it that. Okay. So, this g bar I will write, so that is that, okay, that I can write as okay. Now, this is the known value. Okay. This is something that we have assumed right at the beginning, which was step 1. So, we assume this. Okay. What we are doing here is that first we need to calculate del g del t. So, and this that del g del t is given by 6 to 10, these equations, in which on the right hand side we have the derivatives of the flow properties in space. So, we use forward differences on the right hand side and calculate the derivatives, okay, derivatives at time t from the known values. We do that. So, then we predict the value at the advanced time, which is t plus delta t as so. Okay. Now, in the corrector step, basically what we do is we calculate the derivatives using a backward difference, okay, using backward difference relations using the predicted values. You understand what I am saying? So, in the corrector step, in the corrector step basically, okay, so we basically calculate, okay, now we calculate the derivatives, okay, using backward differences, backward differences using the predicted values. You see the predicted values is at an advanced time. So, therefore, and we are going to call that the derivative as, let me call the derivatives as del g del t. Okay. So, then so in here, okay, so therefore, if I were to write over here, so the average value here, okay, okay, this average value is going to be okay. So, this is the predictor and this is the corrector step, right. So, this is the if you remember right. So, we did this for the we advanced the time, right. We advanced the solution in the r direction, right, for the cone at an angle of attack. In this case, we are advancing it in time. So, then how do we when we march the solution in time. So, okay, similar to what we did in the last scale, time. Okay. So, in this particular case, okay, so the solution will be, okay, let me write it over here. Okay. In this particular case, the solution is going to look like this. So, we are going to base, for example, if we have say r, the value r, or let me call say g. Okay. So, g now, g at an advanced time, okay, is going to be this. Okay. Right. Okay. So, so now what we have done is this del g del t, we have calculated that using a predictor corrector approach, okay, and this is how we advance it in time. Now, again, so once we when we do that, of course, there will be we will there will be errors, okay, and you have to deal with the errors and iterate over it, because we came up with all this solution assuming the flow start at time t. So, clearly that is not the correct flow. So, we will not come up with the correct values in here. So, we will need to iterate, and then the once the once the errors are within a certain tolerance, a limit which you are comfortable with, then your program has, your numerical code that you have written has converged, right. So, if I were to sort of look back a little bit, okay, just to give a comparison. So, this is the time marching. So, I just want you to notice the difference. This is the time difference here. Okay. We have transformed the coordinates. What we are looking at here is we are marching it in time, right. We are marching this in time. So, if you are looking at this particular picture, looking at this particular picture at different instances of time. You understand? You are looking at this picture at different instances of time. We are just marching from this time is equal to 0 to 1 to 2, etc., etc. Okay. What we did in the previous case, we marched the solution in space itself, in the r direction. Okay. So, I will just want to sort of draw a little bit of connection there, if I can. Okay. So, in that particular case, what we had was that instead of this, okay, so we actually, let me draw it here. So, we actually had, say, this is the free stream, right. This is the, so let me draw a cone out here instead of this. Okay. Let me draw this cone at an angle of attack. Okay. Okay. So, this is what we had earlier, right, and so therefore, I said that we are going to march the solution. So, for example, we started off with say R naught, right. So, we went from R1 to R2 here, okay. And the way we said, for example, the okay, let me call, say, properties in this particular case, say density. So, density at, say, R2, okay, and the distance between these R2 is, say, delta R. So, I can say R1, okay, plus delta R, okay, is equal to okay. You see the difference now in this particular, if you see, look at this, and if you look at this, hopefully you can see the difference. In this particular case, like I said, we are marching the solution in time. Okay. So, if you this is a picture, you are looking at every at regular intervals of time, regular instances of time. Here I am actually moving, I am moving in the space, I am moving in space from one radial direction into the other. Okay. So, I am marching the solution in the r direction over here. So, well, I think that sort of concludes the entire this course, which is advanced gas dynamics. So, hopefully you have taken away something from this class. The last bit, I tried to give you an overview of the numerics which is involved in this. The only way we are really going to get a whole picture or understanding, okay, of how to do this is to implement this in a computer program. Okay. So, that calls for an assignment, that calls for rigorous also experience in coding, right. So, however, hopefully you have been able to pick up some things or try to understand a little bit about the physics or the geometry, the 3D geometry, the 3D flow field, which is happening in these three cases, right. So, and we have done basically 3 problems in the 3D case. One is axisymmetric, one is a cone at an angle of attack, and the other is this blunt nose body at an angle of attack, right. And what we have basically seen is that there is a change, there is of course a change in the the physical property of the shock and the body, okay. But numerically it still boils down to, you know, one independent variable, two independent variable. In this case we have a 3D coordinate system, okay. So you can say this is like a truly 3D flow, although the flow is still 3D, whether it's an angle of attack, the cone is an angle of attack like this, or it is a axisymmetric, okay. So okay, I think we'll call it quits there, okay. So you should be able to contact me or ask any questions if you have any suggestions, criticisms, are all welcome, okay, more than welcome actually. And so it should help me to improve next time I do this. So you know, please feel free to contact me, not a problem at all, okay. Thanks.